Hello and welcome to the session where we are looking at obtaining our distribution functions. And we'll do this in two parts. We'll first obtain the distribution function symbolically. So we'll look at the relationship that can give us the distribution function as an analytical function. And we'll also look at it numerically and look at ways to estimate the distribution function as a series of points. So the first step is to just establish the relationship between something that's quite measurable, right? The fraction of a population in a certain property range, that's something we said last time we could estimate and measure in the real world. And the part we were less clear about was the distribution function, which we know is this implicitly defined function. And this was the definition. We said we defined f implicitly such that if you integrate in a certain range, then you get the fraction in that range. And we can look at this relationship and realize that we could differentiate both sides of this equation. So if we differentiate the left-hand side, of course, we get the derivative with respect to the fraction, like so. And if we differentiate the right-hand side, then according to the theorem of calculus, this is nothing but f of x itself. So that gives us the relationship that we're looking for. It's telling us that to get the distribution function, we simply differentiate the function that gives us fractions at the value x. And as much as this looks pretty neat to us, there's a certain conflict that arises. Because in the previous video, we said that we could never define a fraction at a specific property value, right? We always had to integrate between two numbers, x1 and x2. Well, in this case, there is a kind of hidden x1 and x2. So if we define the fraction to be obtained with reference to a specific value, so if, for example, we choose x1 to be some specific number, then we could say we will define x to be the value at the other end. So here we are integrating between x1 and x. So our distribution function is being integrated between x1 and x. So we are integrating over a range still. So we are not violating what we said last time. At the same time, because x1 is now fixed and x is allowed to be variable, that then creates a variable or it creates a function in a single variable x. So this is now our function f of x. And you might think, well, isn't this just a convenience, but it's kind of unnatural because why would you fix the lower limit? Well, you see, there are many properties that do have a lower limit. So, for example, if your property value is the height of a person, then there is a lower limit on the possible heights of a person, right? You can't be smaller than 0 meters tall, right? Or if it's our age, we can't be younger than 0 seconds old. Or if it's the size in radius of something, then it can't be smaller than 0 meters again. So there are many properties that have a minimum value of a 0. And if we do set the lower limit to a 0, then we are asking for all the fractions that are possible up to some value x here. So we are asking, what's the fraction of the population that has a property value of at least x? And you see, that's something that does have a physical intuition. We can imagine many real-world cases where we want to know what's the fraction of people having at least this age. So that is an intuitive and an easy to understand concept if we fix this, if we have a property that has a minimum value of a 0, for example. And it doesn't only have to be a 0. There could well be other cases where the minimum value is not 0, where the minimum value could be a negative number. So, for example, if it's the position of something, an x position can be a negative value if the position turns out to be to the left of our 0. So our minimum value could be negative. Our minimum value could also be positive. It could be that the smallest possible value is not 0, it's 10 or something like that. So we want to integrate it. It makes sense only to integrate from the minimum possible value onwards, right? If there's nothing below the minimum value, then why go and try and add in that region? So we can fix a lower limit, whether it's 0 or whether it's something else. Sometimes, however, we don't even know the lower limit. We just know it's possible to be negative, for example. So if it's possible to be negative, but we don't know how negative, then we can just fix the smallest possible value or the most negative possible value. We could say, let x1 be minus infinity. So as much as this is a less well-defined region, we can set a lower limit like this. And so we can fix a lower limit here, and then we can translate the integral that we introduced last time to one where there's only one free point. And now we have a function in a single variable. And we can do this differentiation. And this differentiation applies at the endpoint, at position x. In other words, we want the derivative at this endpoint. It actually doesn't matter if we are far away from this initial point, right? If we are interested in the value of f at position x, then we only need to consider values near the x point. And so that's what we are looking for. So it is possible to obtain f of x, especially if you start thinking about the lower limit, right? So that's how we can obtain f of x. And that's symbolically how we can do it. So if we have our fractions available as a function, then we can differentiate it. And of course, we don't always have that in the real world. In the real world, quite often, we just have a bunch of measurements. So we may have a series of values for our uppercase f, and we can still then numerically estimate that derivative. So this gradient f, we can obtain it numerically in this way. So we know we want to get df dx, and we can say that df dx is approximately delta f over delta x, and that's equal to this. So that is a way of numerically approximating a derivative. And this instance of it is what we call a left-biased derivative, because we are taking the point I. So we want to know what's the value of the distribution function at point xi. So we can define that value to be fi. So we want to know at the specific value xi, what's the derivative there? So we can obtain that by looking at the value of the fraction at I and the value just to the left of it. And then equivalently, we have to look at the x value at I and the value just to the left, xi minus 1. So that's a left-sided derivative. We could also work on the point I and the point to the right of it, and then we'd be talking about a right-sided bias. So the point just to the right and the point itself. So we are estimating the derivative from those 2 points. Or we could look at the points just to the left and just to the right. So just to the right, I plus 1, just to the left, I minus 1. So those 2 points, and we can estimate the derivative across that. So that's how we can numerically estimate our f values. And here's an example where we have a series of fractions, and it's not just any series of fractions. This is the cumulative series. And so we are saying at position x equals 0, there are no population members having 0, right? And think about the firewood example last time. We were asking what's the fraction of houses having a certain mass of firewood. So when we look at the next value at 5 kilograms, again, we are not looking at specifically 5 kilograms. We are looking at all houses having between 0 and 5 kilograms of firewood. and there are still no houses having just between 0 and 5 kilograms. Then when we start looking at 10 kilograms, then we are asking what's the fraction of houses having between 0 kilograms and 10 kilograms of firewood, and 5% of the houses have that. And then between 0 and 15 kilograms, 10% of houses have that, and so on. So we are dealing with the cumulative integral from 0 to x, right? So the cumulative integral is 0 to x, and so that's what these f's are. And that's why this increases and it reaches a 1, and it can't go beyond a 1, because the maximum fraction is a 1. You've added everything up and you've got a total fraction of 1. So even as you go beyond this, you can't go higher than the 1. So we now have this cumulative f, right, integrated from 0 to x, and we can simply differentiate this function and get our lowercase f. And we can do that with a little bit of Python here. So first, if we just go ahead and plot out the data that was shown, so you can see the zeros here, it increases and then you get to a 1. And then we can numerically estimate the derivative. So you can see the derivative here as we just explained over there. And here I'm actually using the right-sided derivative. So I should be pointing here. So the right-sided derivative, and that's our df dx, and we know that's equal to f. So in this code, I'm just creating a set of lowercase f values. So first initializing with an empty array, and then we just add up all those f values. And if we plot it, you can see there's our distribution function, or those are some specific values of f we have at the given point. Notice here also, if we add up these f values, you can see some fairly small numbers. If we add up all of that, it doesn't add up to a 1, because f itself is not a fraction. We use f to get the fraction, as we said many times last time, but f itself is not going to add up to the 1. But if you integrate under f, then you'll get the 1. And we won't do it now, but if you look under this function here, you can see the values maybe on average around maybe 0.02, and then x around 50, so 0.02 times 50, that will give us the 1. So the area under this is a 1. That will be the total fraction. Okay, so that's how we can numerically estimate our distribution function lowercase f when given a series of values uppercase f. So that's numerically, but in principle, if we also have the function, then it's nothing but the derivative of that function. Thanks for listening.